Hey everybody, and welcome to Control System Analysis and Design. Today I'm going to be going over root locus plots. It's going to be a very conceptual kind of a lecture. I'm just going to go over the basic plots and kind of rules of how you can read them and what you can see from them, and based on what you get and how you get it. So just basic rules, not really any math at all, just graphical stuff. So starting out here, if you've got a root locus diagram like this with a real axis and imaginary axis, the basic things you're able to see is if anything is on this side of the imaginary axis, it's unstable. If anything is on the imaginary axis, then it's marginally stable. And if there's anything to the left of the imaginary axis, then it's all stable. So that's the basic rule right there, just looking at it right off the bat. If there's anything over here, any poles over here, then the system will automatically be unstable. But if all the poles are over on this side, it will always be stable. And then also, as poles on this side, if you have poles moving along here, the more poles, the closer you get to zero, the slower the system becomes. So the more poles closer to zero, the time to the settling time will be greater and greater. Okay, so that should pretty much wrap that up. So working with poles and all that kind of stuff, actually doing the calculations. Like I said, I'm not doing any calculations. But when you're getting poles and asymptotes and that kind of thing to write your locus diagram, when you're getting the angles for the asymptotes, you have to make sure that the number of angles that you get is equal to the number of asymptotes. Asymptotes. Which makes sense because if you have something like this and you've got an x and an x like this, you know that the number of zeros that you need, the number of zeros that you need off in infinity is x, or number of poles, which is 2, minus 0, which is equal to 2. So you need 2 zeros off in infinity. So when you're getting the angle, you need the number of asymptotes that you need is 2. So you know that the number of angles that you need is also 2. So if 2 minus 0 is the number of poles minus the number of zeros is equal to 2, you need 2 asymptotes, you have to have at least 2 angles. So usually when you're doing the theta over here, you're going to end up with a plus or minus like pi over 2 or something like that at n equal to 1. And you can look up that formula to see how that works. But just remember that the number of angles that you get has to equal the number of asymptotes. And it's plus or minus because of symmetry, because if you have a pole up here, then you have to have a pole down here. That's another rule up here. Everything has to still be symmetric no matter what. If there's a pole you put up here, its exact opposite has to be down here, just because of the quadratic equation, the whole plus or minus deal. Alrighty. So, I'm going to do a quick example here. Let's see what I got. So, looking at this root locus diagram right here. What you can see, let me get myself arranged so I do this correctly. So I've got 2 poles right here. They are symmetric, which has to be true. And then you've got zeros on the real axis. Now, what can you do? When you actually look at this problem, there were no asymptotes associated with this. And the reason you know there's no asymptotes is because each x goes to a 0. They're equal to 0. So 2 minus 2, 2 poles minus 2 zeros is equal to 0. So there's no asymptotes. But you have these x's up here. So how do you draw the x's to the zeros in order to follow root locus criteria? Well, in that case, if there's no asymptotes and you have an x on the imaginary axis, you draw just a straight line. So the point of this is that in order to get to 0, you draw a straight line right down to the real axis, and then you split off like this. So both of these x's go just like this, and then they split off like this after setting it there. Now, another comment with that, well, no, I'll do a different one here. Alrighty, I'm going to draw a different picture here. If you have asymptotes, if you've got like an x here and an x here, and you've got an asymptote going like this and an x here, you've got an asymptote going out like this, which you'd find by doing the theta equation, find the asymptotes. But then you've got this x going like this, which is going to go out like this, like this. A couple things I want to point out right here. I'm actually going to draw another picture to make this a little bit clearer. You got an X right here, an X right here, going right here, and then an X right here, and an X right here, or poles right here, and then the asymptotes are like this. You might wonder exactly where when these split off, which they have to do in order to go to zeros, they have to go to the asymptotes. How do you know if this X goes over to this asymptote and this X goes over to this asymptote or something similar like that? Well, there's no real hard set rule on that. It's basically just do what's easy. So that these zeros are going to stay within these poles are going to stay within these asymptotes, and these poles are going to stay in these asymptotes. They are not going to like go funky and do something like this, and then cross over or anything like that. So you don't ever have to worry about discontinuities on the asymptotes. That just won't ever really happen. Just assume the easy thing happens. Anything on these asymptotes stays on these side of the asymptotes. Okay, and then looking in at these right here. So do these approach each other or do they actually intersect? Well, if you zoom in right there and you're looking at the real axis, and you've got the pole over here and the pole over here somewhere, and you've got it all filled up here, and they're coming together, and then you're going to have jet off to the side here, kind of like that somewhere, and like that to go to the asymptotes. What's happening in here? Well, they actually do come to a point. They both sets of zeros come to a single point and then shoot off to the side. And if you use a program, you may or may not see that depending on how small your intervals are. But it does come to a point. If you ever did something or drew something that does like this, and then this comes down here like this and comes over like that, that is wrong. That is not how it works. These points, the zeros actually intersect as the game moves around. Alright, so now, moving off from there, okay, so here's another root locus diagram. Now we're going to actually interpret what this root locus diagram means. So we have a 0 at the origin. Since we have a 0 at the origin, no poles at the origin, you can immediately assume that it's a type 0 system. So for your steady state error is going to equal a constant. So the error is going to equal a constant k, because you don't have any poles at the origin. Now moving on from that, as k, as your gain, if you move, the only way you can interpret this is by moving the gain around. So as k goes to gets greater, you'll see that you kind of spread out because this one's going to this 0, and these are going off to here. Well, you're going to say that this is actually going to be a system that's slow and gets slower. Remember how earlier I said that with this picture, as you move closer to the origin, everything gets slower? Well, if you look at this, there's a dominant system right here, in this picture. This is actually something you're almost going to ignore because it's so far to the left axis that its impact on the system as a whole doesn't really matter. So you're actually going to focus on this half of the system, and you'll see that X is kind of close to the origin, so it's going to be a fairly slow system. But then as K increases, as your gain increases, it's going to get slower because you're going to get closer and closer to the origin. And then, in addition to that, you see that you only have one pole that really matters, so you can estimate this, approximate it as a first-order system. First-order system. As K gets larger. As K gets smaller, well, then you're going to have a little more impact here because you're going to have a real system down here, and it's going to come down here, and so on and so forth. But again, you can still almost ignore this half and just imagine it as a single system that's getting faster as K gets smaller. So that's a basic little rule there for you to look at and see. Alrighty, let me draw another one more here to illustrate this a little bit again. So say we've got this system right here, and this time we have a pole on the origin, pole right there, pole right here, and pole right here. So you're going to fill those in. I'm going to say I have an asymptote right there, and an asymptote right there. It doesn't really matter. And then they're going to go off like this or something. I'm going to Make that an asymptote like that. Okay, and those are all filled in right there. It's going off to infinity, and this is going off to infinity along the asymptote. So kind of a rough drawing, but you get the point. Pole right there, pole right there. So as k gets greater, becomes greater, you'll see that this is the smallest k. These x's right here is the smallest k you'll get, and they're the k for the closed loop poles. The original x's and zeros that you draw on the graph are the closed loop poles, and then anything on these lines is the open loop poles. And you learned about those earlier. I just want to make that clear to you. But as k gets greater, you're going to move from these poles, and then you're going to move into space on these zeros. And it's coming in here, and then we split off on these graphs. So as k gets bigger and bigger, well, you start to see a second order system start to form. So it becomes a second order system. Second order system as k gets bigger. But then, as you keep on going, you see you're going to cross the j omega axis, the imaginary axis. So you're going to have poles over on this side of the root locus diagram, which means it's going to become unstable after a point. And you can calculate where it crosses and where that point is, but we're not going to go into that. But you can classify it as basically a second order system that's going up, and then becomes unstable as k gets greater, becomes greater and greater. But then again, you ignore this part because it's basically so far to the left that as this becomes greater and greater, these poles move way out here, so the separation is so great from these poles that you can basically ignore them. So if k gets smaller and smaller, k goes smaller, let me write that, k goes smaller, well then you're coming back here and you're shrinking down to these zeros and zeros and zeros and zeros. And in this case, depending on how far apart these two poles are spaced, you're still going to kind of ignore it, but you're going to almost model it as a first order system, because as these get closer and closer to these poles, you can come to ignore this pole and just imagine the response at this one right here. So it's almost a first order response. It tends towards a first order response as k's get smaller, because you're focusing more and more in on this pole, and this pole is becoming less and less relevant because it's basically moving down the axis as you're getting closer and closer. So let's see if I hit everything there. That's about it. Yeah. And also, if you got poles on the real axis, you're going to almost immediately assume it behaves like a first order, just because on the real axis you don't have any oscillation. So if you've got two poles on the real axis, the kind of response you're going to get is something almost like this. But as soon as you move off of the real axis, off of this horizontal line, then you start to get some kind of overshoot and this kind of thing, the oscillation and so on and so forth, and settling time. So as long as you're on the real axis, you're going to have an overdamped situation, which almost looks like a first order response, so you can take that first pole. That's why that's able to work. As long as you're on the real axis, it's pretty much always going to be a first order response. Technically it's the second order, because technically you still have these poles there, but as an approximation it's okay to use a first order response. And that is it. Okay, hopefully that kind of helped you understand how locus diagrams are read and why certain things happen the way they happen. I'll do another video where we actually do the calculations, and maybe another one of these where we get into more graphs.